You know it. My propeller, Arctic Monkeys. Very appropriate as we are doing induced current, which is how we deal with all electric motors. And so motors make propellers go around. That's what today's video is all about. Before we get to induced current though, let's do a little bit of a right hand rule practice. There's 3 of them up here for you to do. If you want, pause the video, figure out which way they go, and then I'm going to work through them. I think I'm going to do them, let's do them in green today. So I know this is a minus up here. Oh, I need to change it to, now this is a minus up here. And that means that my plus is down here where this ground is, because ground can be either plus or minus, remember. And so I'm going to go away from this plus, which is my ground, and then I'm going to draw my little arrows on all these. I'm going to do my right hand rule, fingers curl around, which says that my big arrow in the middle is going that way, always points towards north, away from south. And so that's my first right hand rule practice. On the next one, I have a current that's going around in this direction, and so I can take my hand, the curvy thing is that current, and so I do my hand and my thumb then points towards the center, and so that's a circle with an X, that's a magnetic field in the middle. That's usually what I'm looking for. If I was looking for the outside one, I'd make it go the other way, so I could put circles and dots all the way around the outside. But really, I'm looking for that middle one. The direction of the circle for the last one, I'm going to take my fingers, put them in the direction of the magnetic field, which is into the page. My thumb, put it in the direction of the velocity, which is that way. So my force shows my palm shows the force goes upwards, which means that's my F. That's my F and that's my V. It's going to cause this thing to go around in this direction in a circle, and so I could say counter clockwise. That's for the right hand rule. So earlier when I was doing these videos, I told you that all magnetic fields was created by charge moving. And it turns out the inverse is true as well, that magnetic field can create a current. They're very much intricately related, those two. And it turns out that anytime we have a change in the magnetic field. Oh, look, there's a spelling error. Ooh, gotta change that. I'm just gonna put spelling F-E field. Yeah, don't get that wrong. It doesn't look right that way either, but it's just my handwriting, I think, at this point. Anyway, any change in magnetic field through a closed loop of a conductor creates a current. And so that means that if I have some kind of area, let's call that an area, and I have no magnetic field, and all of a sudden I put some magnetic field through it, that will create a current in the wire around which the current is through. And that's the basis of all of electromagnetic conducting, but we need to talk a little more about the specifics to get the numbers for that current. So to do that, we have to have some kind of measurement of the amount of magnetic field that's through some closed area. And the thing we use for that is called magnetic flux. It's the amount of field going through a given area. And so if we have a certain area, like this area over here, and we put a normal on there, which is 90 degrees to my surface, and we call that the direction of my area. And the area would, just take the length times width to get the area, or if we're doing a circle, we can do pi r squared. But to get the flux, we take the magnetic field times the area times the cosine of theta to get the amount of flux going through there. And a lot of times, the flux going that way, the magnetic field going that way and the area going the same direction, the cosine of 0 would then be 1. This often goes to nothing, and my flux becomes BA when the theta is 0. Notice the magnetic field in Teslas. My flux is measured in Webers, another famous guy that worked in magnetism, got his name on something. And then there's some examples of the flux here. This one down here has an angle in between the two of them. So like if this is a side view of your area, and then your magnetic field is going this way, your normal to the area goes at 90 degrees. This would be your theta between the normal and the magnetic field. That's it for flux. Like I said earlier, it's a change in that flux that creates a magnetic field. So if the flux is the same through an area, you got no potential difference, no voltage created there. But if we have a change in the flux over time, then we get an EMF. And an EMF is my raw voltage, remember. And I have to know how much that flux changes per time, and that tells me what the potential difference, the V that I put into my V equals IR would be. And I can change that flux a lot of different ways. I'm going to go through a bunch of different options for you on how we change it, and then talk about how that creates a current for us in the couple examples that I have coming up. One change in flux is used so often that they put the formula on the formula chart for us, so you have to memorize it. And that is the situation that I like to refer to as a railgun. I say refer to it as that because it's not really a gun, but it is a rail. The way we talk about it first is that we move it to create a current. The gun part is when you put a current in to make motion, but let's first talk about it the way where we create the EMF, because that's the way our equation is written. And so basically I'm going to have three sides of conductor and then a bar that goes across them that's movable. And then I'm going to take that movable thing and move it in one direction or other. In this case, I'm moving it to the right there. And that's going to make more and more flux go through my loop, because this is my loop here, and more flux is going to go through it as I move that to the right. More and more X's, which is my magnetic field, are going through it. So there's a change in the flux through the loop, and so that's going to create an EMF. The equation is given by that right there. And to just derive that fairly quickly, we know that flux is B times A. And since the B isn't changing in this one, it's going to be B times delta A. And my area is going to be the length, which is the length of the bar, this right here, times X, which is my distance right here. And the X is the one that's going to move. L isn't changing. So this then becomes B L delta X. My X doesn't want to go through it. All right. And so that's my flux. And so then I take that to get EMF. I take it divided by delta T. I divide this by delta T. And then fairly quickly we can see that delta X over delta T is V. Thus we get our nice B L V for that EMF. Just a quick derivation of that. The negative that's in there is basically telling us the direction of the current, and we're going to find that with another method. So for practical purposes, when we use this equation, we just find the value of B, which is the magnetic field, times L, which is the length of the bar that's across right here, times the velocity that the bar is taken to the right. So here's where it gets a little strange and conceptually. As the bar is taken to the right, more and more X magnetic field is put in that loop. Now when we create a current in there, we're getting energy out. To do that, we should be putting energy in, because we know that energy is never created or destroyed. And there's an easy way for us to figure out the direction of the current. Because what happens is we can take and say, okay, if we're putting more and more X's in there, the way to make that difficult would be to put magnetic field that's the opposite direction in the middle of that. And so we take the same picture, the same bar graph, but we put the opposite magnetic field. So the opposite of what's happening. If we put more and more X's to resist that, we would put circles with dots in the middle of that. And then what would create that magnetic field, we can take our right-hand rule, take our thumb out of the page, our fingers curl around, and since that's a straight thing, our fingers would curl around this way, creating the current that would be induced there. And we call it inducing. I think I put creates up there first, but I like the word induced better. So that's what we talk about, the current being created is called induced. Now that's a little weird. Why is it creating exactly the exact opposite magnetic field? Again, it gets into a little more math than we need to know for this particular class. There's a lot of calculus involved. I know I just throw that word around a lot. But it's an easy way for us to get the direction of the current. So for any kind of induced current, we are going to find what's happening, in this case x's, do the opposite, dots, do a right-hand rule to find what would create those dots. That's the way that my current would be created in this circuit. Snack time. If you've been paying attention to this unit, you know that the snack theme is things that my mother gave me as a snack as I was growing up. And I don't know if you've noticed, but they've all been fairly healthy. My mom was really into all the whole grains, natural food stuff, long before it was actually popular or any of my friends had to endure it. They all got Kool-Aid. I got milk, pretty much exclusively. It turns out that my mom was right, theirs wasn't. But this was all when my mom was a stay-at-home mom, and when I got into high school, she went back to school. She got a degree in computer science, and she's going to school pretty much full-time, and so things changed. And she didn't have quite as much time to fix stuff, and every now and then we got the good stuff. And so things changed a bit. And so today's snack was one of my very, very favorite ones from my mom. There is cantaloupe, and the cantaloupe is fairly good for you. And that was her whole excuse for this. But there was a dinner that we had one night that was cantaloupe, but not just cantaloupe. We took the cantaloupe and we scooped all the seeds out and we used it as a bowl, and we had ice cream in cantaloupe for our dinner. Nothing else, just the cantaloupe in the ice cream. And it was amazing after all those liver dinners, all that stuff we had to eat. Ice cream. And today's ice cream is Breyers, vanilla bean, French vanilla. Very, very, very good. One of my favorites. Also gluten-free for those people that have that thing to worry about. I am having ice cream for the first time in a long time because most ice cream I can't have, but this I can. Ice cream in a cantaloupe bowl. Nothing better. Good stuff. Give it a try. So I'm going to run through a bunch of different induced current things. And the first one is going to be if a loop that has no magnetic field into it is pushed into a big magnetic field. And I would make this probably bigger, you know, a bunch of circles with dots in it. But as this is moving over, notice that we have a length L being moved over at a velocity V. And so this ends up being just like the railgun problem. Even though it's not a rail, there's not a rail in there, but we know that our flux is going to be BA, and I could put the angle on there, but I know it's at 90 degrees, so it's going to go away. And so I get B, and the area is going to be the length times the change in X, length times width. And then to get the EMF, I take the change in that over the change in time. So I get BL delta X divided by delta T. These two change into BLV, and I get the exact same equation. So anytime I have a vertical or any kind of bar that's at 90 degrees to what I'm pushing it into or out of, I use that exact same equation. And this one, to find the direction, I would say as I move that into the field, I get more and more circles with dots in that. I draw a picture, and I do the exact opposite. Opposite of that, I put a circle with an X. I take my right hand, put it in X, and my induced current would go this way. And so again, I just do the opposite of what's happening, and that tells me that my I that's induced is that. My EMF would be BLV. If they told me that the resistance on this wire was some number, I could do also V equals IR with that resistance and the EMF there to find what the current would be. For my next induced current, I'm going to say that my loop of current doesn't change. Let's say it's 2 meters by 2 meters, and it doesn't change at all, but I'm going to change the magnetic field that goes through it and see how much current is induced by that. So I need to do flux first. I know that flux is B times A, the B being 5 times the change in time, my area being 2 times 2 or 4, I get 20 delta T for my flux. And then I want to take the change in flux over the change in time to get my weird little EMF. And so I get 20 delta t divided by delta t. Those cancel, and so I end up with 20 volts induced in that particular loop by changing the magnetic field inside. Now to get the direction, I see what's happening there. I get more and more outbound flux through there, and so to resist that, I put one in, take my thumb, go in, my fingers curl around, and the induced current is going to go in that direction with a potential difference of 20 volts. If they give me the resistance, let's say they put a resistor of 2 ohms on there, I could do V equals IR, which would be 20 equals I times 2, and my I then would be 10 amps. That's how I do that kind of problem. If instead my magnetic field stays the same and I make my area change as time goes on, I do something very similar. My flux then becomes, again, BA. This goes away because they're in the same direction. And so then my magnetic field doesn't change. Let's say it's 5 Tesla. I go 5 times 3 delta T. And then to get my EMF, it's change in flux divided by change in time. So then I get 5 times 3 are 15 delta T divided by delta T, cancels, and I get 15 volts. And if I want to figure out which direction that is, I say if as that gets bigger, more X's go in there. If I get more X's to resist that, I would put dots to my right hand rule, my fingers curl around, and my direction of current in this case would be counterclockwise. So the last one I'm going to do is going to be a loop of current, or more ice cream, good show. Loop of current in a magnetic field that spins. And this time, in our flux thing, we have BA cosine theta. It's the cosine theta that changes this time with respect to time. And so that loop going around will get us a current because a different amount of it is going through the loop. So as it turns, let's say it's going clockwise from above, so that's going back and this is going forward. It creates a current in there. And we can figure out which way it's going by looking at the fact that as it turns a little bit that way, in the next second, those ones are going to be going into it. And so I'll have more in the next couple seconds. And so I resist that by coming out to my right hand rule. And so the induced current goes that way. And it turns out that as it gets past a certain point, it'll go back the other way. And so this induces a nice sine wave current, which is alternating current, which is what's created by every generator that we make. That's about it for induced current. Congratulations, you're done. All right, that's about it for this particular unit. It's the last unit. One more butter ice cream, one more propeller head, and you're off.